whenever you sit down and fire up a chat with an AI like Grok or
ChatGPT.
right, or even when you just let Netflix seamlessly recommend that exact movie you didn't even know you wanted to watch.
It's a great feeling.
It is. Or, I mean, seeing an autonomous car navigate a super chaotic city intersection, it just it feels like magic.
It really does. It's totally sci-fi.
Exactly. You look at it and think, we are absolutely living in the science fiction future,
Yeah.
but, and this is the crazy part, what if I told you that the secret behind all of this futuristic magic isn't actually magic at all?
Spoiler alert, it's not.
Yeah. What if the invisible engine driving the absolute most advanced technology on the planet is essentially high school math?
It's a bit of a reality check, honestly. I mean, we dress the whole field up in these fancy terms like artificial intelligence and machine learning, which,
Sound incredibly mysterious.
yeah, almost biological, right? Like we're building a brain. But when you strip away all the marketing and you look at the foundational level, we are basically just talking about linear algebra.
And that is our mission for this deep dive. We are going to completely unmask this invisible engine of artificial intelligence.
We really want to prove to you that linear algebra is not, some abstract academic punishment designed to just torture teenagers.
Right, it's actually an elegant, highly accessible superpower. And to do this, we've pulled together an incredible stack of sources for our deep dive today.
We really have. We're looking at the foundational 2020 textbook, Mathematics for Machine Learning.
That's the one by Dijzenroth, Faisal, and Ong, right?
That's the one. And we've also got some technical briefs and really good explanations from IBM.
Plus, we are pulling concepts from the legendary Gilbert Strang and his MIT courses.
It's just a fantastic collection of materials. It really bridges that gap between the highly theoretical math and the actual practical applications that you, the listener, interact with every single day.
So yeah, we're speaking directly to you. We promise you a journey full of aha moments today. No overwhelming jargon, just the beautiful mechanics of how machines actually learn.
It's going to be fun.
Okay, let's unpack this. Before an AI can learn anything at all, it needs a way to, read the world, right?
Yeah, because a computer obviously doesn't have eyes or ears.
Right, it only understands numbers. So the very first hurdle is translation.
And the real world is messy. I mean, it's totally unstructured. It's full of images, text, chaotic user preferences, fluctuating sensor readings.
Just pure chaos.
Exactly.
Yeah.
So how do we force that messy reality into a format that a machine can actually process? This is where our first mathematical building blocks come in.
Vectors and matrices.
Vectors and matrices, exactly.
The sources gave me a really cool framework for this, and I kind of want to try visualizing it. Think of all the raw data out there as ingredients in a massive kitchen.
Okay, I like that.
So if you just have a massive pile of flour and eggs and sugar, it's just chaos. A vector is basically a way to organize those ingredients into a single ordered list.
Right.
So if we look at your Netflix profile, for example, Netflix doesn't know you as a human being with a soul and a complex childhood.
Thankfully.
Right, thankfully. It knows you as a vector. So your vector might look like a simple list of numbers and brackets, like 28, 4.2, 87.
Let's actually define what those numbers mean in that mathematical space. So the 28 could be your age.
Okay.
The 4.2 could be your average star rating across all the comedies you've watched.
Makes sense.
And the 87 might represent the number of hours you actually spent watching Netflix this month.
Which is a lot of hours, but no judgment.
Hey, we've all been there. But mathematically, this ordered list is represented as just a single point in a vast geometric space.
Okay, so that's a vector, a single user.
Right. Now, if a vector is one user's profile, a matrix is simply the massive spreadsheet containing millions of those vectors.
Got it. So an entire data set of Netflix users is a matrix with rows representing the users and columns representing their specific features.
Exactly. So the matrix is basically the master inventory list.
But just having a list doesn't actually do anything, right?
Yeah.
The Mathematics for Machine Learning book has said something really specific here that stood out to me.
Oh, about transformations.
Yeah. It says matrices encode linear transformations.
Yeah.
That tells me that multiplying a matrix by a vector isn't just crunching numbers for the sake of it.
No, it's doing an action.
Right. It's doing an action to the data. It's like, okay, think of passing an image through an Instagram filter, but you're using math.
That's a really good way to put it.
You multiply the image data by a specific matrix, and suddenly the math literally, physically alters the pixels. The image is blurred or sharpened or the colors get supersaturated.
And it goes way beyond just transforming data into a new shape. These mathematical operations allow the system to compare entirely different concepts. Take the dot product between two vectors. This is a super fundamental operation where you mathematically multiply and add the corresponding numbers in, say, your profile vector and your neighbor's profile
Oh,
vector.
wait, let me make sure I'm visualizing this right.
Sure.
If my profile is an arrow pointing somewhere in a giant 3D space, and my neighbor's profile is another arrow,
Yep, keep going.
the dot product is basically the math figuring out if our arrows are pointing in the exact same direction.
Yeah, it is a perfect way to picture it. It measures alignment.
Wow.
Yeah, if the dot product is a really high number, your arrows are highly aligned. That means the platform mathematically determines that you and your neighbor have the exact same taste in, I don't know, obscure documentaries.
But it doesn't know why we both like them.
No, not at all. It just knows your vectors point the same way.
Man, it's a little unsettling to realize that my highly specific, unique movie taste is literally just a geometric alignment of two arrows.
Welcome to the Matrix.
Right. Okay, so now we know how the machine reads the data using vectors and matrices. How do we use those organized ingredients to actually predict something?
Well, the sources point us to the oldest trick in the book.
Linear regression.
Exactly. The absolute grandfather of machine learning.
So before we had massive language models writing poetry and coding websites, we had linear regression.
And honestly, it's still the backbone of predictive modeling today. Let's say you want to predict the price of a house.
Okay, classic example.
You have a matrix of features, which is the data we already know, like
Right.
square footage, the number of bedrooms, the distance to the nearest school.
Right.
The goal of the machine is to multiply that feature matrix by a weight vector.
Okay, let's pause on that word for a second. Weights. I like to imagine weights like the volume sliders on a giant audio mixing board.
Oh, I like that analogy.
Yeah, so the machine has to figure out exactly where to push each individual slider. Does the square footage slider need to be pushed all the way up because it's super important for the house price?
Usually, yes.
Right. And does the proximity to a busy highway slider need to be pulled way down because it hurts value?
Exactly. The machine is trying to find the perfect arrangement of all those sliders.
And how did it do that?
To find that perfect arrangement, the machine relies purely on the mechanics of linear algebra. Chapter 9 of the Mathematics for Machine Learning book actually dedicates an enormous amount of space to deriving this step by step.
I saw that. It's pretty dense.
It is, but the concept is beautiful. To find the absolute best weights, the ones that produce the lowest possible error in our predictions, we have to solve what are called the normal equations.
Normal equations, okay.
We don't need to read the raw algebra aloud, but geometrically, imagine dipping into a valley of errors.
A valley of errors, okay.
Calculus tells you which direction is downhill. But getting to the absolute bottom of that valley, the point of lowest error, requires taking your feature matrix, flipping it sideways, multiplying it by itself, and then doing a matrix inversion.
Hold on, I want to push back on this for a second.
Go for it.
Are you saying that without doing these foundational, almost rudimentary algebral steps, things like matrix inversion or Gaussian elimination, that people learn in their first year of college,
Yeah.
there is literally no prediction? The machine just stops.
Completely. Without the ability to flip that matrix, multiply it, and invert it, the machine is completely blind.
Why?
There is no learning happening. There is no artificial intelligence magically finding the bottom of that error valley. It is purely linear algebra turning the crank.
That brings up a really big question for me then.
What's that?
If linear regression is the grandfather, predicting house prices by inverting a relatively small matrix,
Yeah.
how do we get from a simple valley of errors to the modern magic?
Right, the big stuff.
Yeah, how do we get to massive systems like ChatGPT or Grok?
We get there by taking that exact same basic concept, multiplying matrices and vectors, and doing it on an absolute industrial scale. We step into the world of deep neural networks. The core equation of a single layer inside a neural network is still just a giant matrix vector multiplication, plus a little numerical nudge called a bias.
So if we take my old chef analogy, actually, you know what? The chef analogy breaks down here because a chef just mixes things once.
Yeah, neural networks are way more layered than that.
The sources describe neural networks as having layers upon layers. So think of it more like a massive game of telephone playing out in a giant stadium.
Oh, a stadium. Okay.
The first row of people looks at a raw image and whispers, "I see a curved line," to the row behind them. The matrices act as the strict rules, dictating exactly who listens to whom and how loud they whisper.
That stadium visualization actually captures the structure really well, but here is the critical twist that makes deep learning actually work.
Okay, what's the twist?
If every row in your stadium only ever did pure matrix multiplication, the math dictates that the entire stadium of whispers would just collapse down into one single flat linear equation.
Wait, really? It just flattens out.
Completely. It wouldn't matter if you had 100 layers or 1,000. The output would mathematically just be a straight line.
So how do they fix that?
To fix this, after every single matrix multiplication, the data is forced through a nonlinear function.
Okay.
It's something with a fancy name like ReLU or a sigmoid curve.
A nonlinear function. So that's the machine throwing a curveball.
Exactly.
It allows the network to learn totally unpredictable, jagged, complex patterns like recognizing the specific shape of a dog's ear instead of just drawing straight lines through data.
Spot on. And then that output becomes the input for the next row in the stadium and the next.
That is wild.
What's really fascinating here is the sheer unimaginable scale of the operation. When we talk about a deep neural network with millions or even billions of parameters, we are talking about a system executing billions of these matrix vector multiplications every single second.
Billions per second.
Yes. Gilbert Strang from MIT explicitly calls linear algebra the language of neural networks. If you don't speak the language of matrices, you simply cannot build or understand a modern AI.
But wait. If AI is doing billions of calculations per second on data sets that might have thousands and thousands of columns, wouldn't the system just choke on all that data?
What do you mean?
I mean, if I give a model a data set with 10,000 highly detailed features for every single user, doesn't the math just become too heavy to lift?
It's actually way worse than just being too heavy. IBM's technical documentation explicitly highlights this as one of the most notorious traps in data science.
Really? What do they call it?
They call it the curse of dimensionality.
The curse of dimensionality. That sounds like a sci-fi horror movie where the characters get trapped in a tesseract or something.
It really does. And it's a very real trap for computer scientists. It's not just about the processing weight, it's about physical distance in mathematical space. When your data has too many dimensions, say 10,000 columns, the geometric space becomes so unimaginably vast that your data points are left floating millions of miles away from each other.
So the space is mostly just empty.
Exactly. It's sparse.
So because the data points are so insanely isolated, the AI can't actually see the forest for the trees.
Right.
It just memorizes the exact location of every single tree, which is really just random noise, instead of learning the actual underlying pattern we want it to learn.
Yes, and that leads to massive overfitting. The model works perfectly on the training data in the lab, but it fails completely out in the real world.
Oh, wow. So how do we fix it?
To break the curse, we need a mathematical trick to reduce the dimensions without losing the actual meaning of the data. And that trick is PCA.
Principal component analysis.
You got it.
Okay, let's unpack this. How does PCA actually work without just, randomly deleting columns of data and hoping for the best?
Well, it relies on calculating what's called a covariance matrix.
A covariance matrix.
Yeah, it sounds scary, but it's basically a grid that measures how every single feature stretches and squishes in relation to every other feature. But instead of getting bogged down in the algebra, imagine you have a 3D cloud of data points just floating in the air.
Like a swarm of bees.
Sure, a swarm of bees. If you shine a flashlight on that swarm from the front, it casts a shadow on the wall, right?
Right.
If you walk around the room and shine the flashlight from different angles, the shape of the shadow changes.
Obviously, yeah.
PCA is the mathematical process of rotating that cloud of data, the bees, until you find the exact angle where the shadow is spread out the absolute widest.
Oh.
That specific angle, the one that captures the most shape and the most variance, is your principal component.
Oh, wow. That is such a good visual. So you find the widest angle and you keep that specific perspective.
Exactly.
And any angle where the shadow just looks like a tiny compressed dot, you just throw that perspective entirely away because it doesn't hold any useful information.
You don't need it.
So we are taking a data set that has 1,000 dimensions, and we are rotating it and squishing it down to just 50 dimensions. But miraculously, we are keeping 95% of the original shape of the data.
IBM explains it beautifully in their docs. PCA projects the data onto these principal components specifically to capture the maximum variance, all while throwing away the redundant noise.
That's incredible.
You cure the curse of dimensionality by shrinking the space intelligently, keeping only the angles that actually matter.
That's brilliant. It's like summarizing a 500-page novel into a 10-page cheat sheet, but somehow not losing any of the actual plot twists.
Pretty much.
But wait, if PCA is so great at shrinking data, why does Netflix need something totally different?
Ah, good question.
Let's bring this back to Friday night, sitting on the couch, deciding what movie to watch. Netflix uses a different math trick, right?
They do. For recommendation engines, we turn to a sibling of PCA, a concept called singular value decomposition, or SVD.
SVD. Okay.
Gilbert Strang actually dubs SVD the fundamental theorem of linear algebra.
That's a huge title.
Yeah. It is. PCA is fantastic, but it assumes your data is relatively complete. Think about the raw data Netflix actually has.
Okay.
It's a massive, clunky matrix with hundreds of millions of users as rows and tens of thousands of movies as columns.
Right, and most of that matrix is completely empty space because, I mean, I haven't watched 99.9% of the movies on Netflix.
Nobody has.
So if you shine a flashlight on that swarm of bees, you don't get a shadow. You just get a whole lot of blank wall.
Exactly the problem. The data set is too big and way too sparse for standard tricks.
So what does SVD do differently?
What SVD does is take that one giant, mostly empty user movie matrix and physically forces it through a mathematical bottleneck.
A bottleneck.
Yeah, it breaks it apart into three much smaller, incredibly dense matrices.
So how does breaking it into three dense matrices help Netflix know that I want to watch a specific movie tonight?
By squeezing the data through that bottleneck, SVD isolates what data scientists call latent tastes or latent features.
Latent tastes? Let me try to map this out.
Go for it.
So if I really like The Matrix, and I also really like Inception,
Two great movies.
the math notices that millions of other users who rate those two movies highly also tend to give 5 stars to Blade Runner.
Exactly.
The machine obviously doesn't know the English word cerebral sci-fi.
No, it has no idea what genre is.
It just creates a new, completely invisible category, a mathematical cluster of overlapping numbers, and assigns value to it.
And to take that visualization a step further, those three smaller matrices perfectly capture that invisible category.
How so?
One small matrix represents how much you, the user, align with that hidden cerebral sci-fi cluster.
Okay.
Another matrix represents how much the movie Blade Runner contains that specific cluster.
Oh, wow.
Right. By multiplying those dense, smaller matrices back together, the system bridges the empty space. It mathematically predicts your exact rating for a movie you haven't even seen yet.
So it's clustering overlapping numbers to find a pattern I don't even have a name for. It's literally reading my mind by finding the geometric center of my watch history.
That is the Netflix mind-reading trick, powered entirely by the fundamental theorem of linear algebra.
Okay, I'm fully sold. The math is incredibly powerful. But if this math is so foundational, what is actually holding the industry back?
What do you mean?
Like, what are the real-world challenges that everyday programmers and data scientists are facing right now?
Well, the very first challenge is simply overcoming the abstraction of it all.
The math itself.
Yeah. When you look at pages of textbook equations in mathematics for machine learning, it's incredibly easy to feel totally intimidated. Human brains are just not wired to easily visualize a 100-dimensional space.
No, definitely not.
Or to mentally track the transposition of a million-row matrix.
Oh, absolutely. The listener right now might be thinking, I get the flashlight and shadow analogy, but looking at a page of Greek letters is terrifying.
It is terrifying.
But the sources actually offer a great solution for this. We don't have to stay stuck in the textbook trying to decipher equations.
Right. There are amazing, completely free visual tools out there now.
The 3 Blue 1 Brown video series on YouTube is legendary for this. It graphically animates exactly what these matrices are doing to space. You literally watch the grid stretch and skew in real time.
It's mesmerizing, and Gilbert Strang's entire MIT linear algebra course is available for free on MIT OpenCourseWare.
Those visual resources are invaluable for building an intuitive geometric understanding rather than just doing rote memorization.
Exactly. But beyond just the conceptual abstraction, the field is facing very real, hard physical limits right now.
Physical limits? Like what?
Specifically, compute limits. We mentioned earlier that modern models have billions of parameters.
Right.
To handle that much math, the field can't use standard computer processors anymore. They rely heavily on highly specialized hardware, specifically GPUs.
Right, so the graphics card in a computer isn't just for rendering highly detailed video games anymore. It's fundamentally a massive matrix multiplication engine.
That's exactly what it is. And programmers rely on software frameworks like TensorFlow and PyTorch to manage this math across thousands of GPUs simultaneously. But here's the kicker. Even with all that hardware, models are still getting too big.
So what do they do?
They actively use techniques like low-rank approximation, which leverages that exact SVD concept we just talked about to compress the models so they can run faster and cheaper.
Ah, full circle.
Yeah, they use PCA every single day to combat the curse of dimensionality and keep compute costs from literally bankrupting the project.
It feels like the entire industry is in a constant tug of war. We want bigger models with more parameters to get smarter AI, but we are constantly bumping up against the physical limits of how many matrix multiplications we can physically perform on silicon chips.
Without melting them, yeah.
Right, without starting a fire.
And if we connect this to the bigger picture, the sources point to a fascinating future challenge for the whole field.
What's that?
We have pushed traditional silicon almost to its absolute physical limits. The question the industry is facing now is, how will linear algebra scale with entirely new paradigms?
Like quantum computing.
Exactly. Quantum computing, or neuromorphic AI, which is hardware that actually attempts to mimic the physical structure of the biological brain.
Oh, wow.
So the big question is, will the foundational math remain exactly the same, or will we need a completely new mathematical language to bridge the gap?
That is a wild thought. We're just getting a handle on managing billions of parameters, and the fundamental hardware rules might change completely in the next decade.
It's moving fast.
It really is.
But for now, let's sort of recap our journey today.
Let's do it.
We started by looking at AI as this impenetrable dark magic, but we've seen that it's anything but.
No magic involved.
Right. From the simple prediction of a house price by dipping into a valley of errors, all the way to massive neural networks playing a stadium-sized game of telephone to power ChatGPT. It is all an elegant army of matrices, vectors, and linear transformations working tirelessly behind the scenes.
The Mathematics for Machine Learning book really summarizes the reality of the field perfectly.
What do they say? They emphasize that linear algebra provides the exact, precise tools needed to organize, manipulate, and analyze massive amounts of data efficiently at scale. Without it, the modern world of data simply collapses under its own unstructured weight.
And the best part is, you, the listener, can actually take control of this invisible engine yourself.
Absolutely.
You don't need a multi-million-dollar supercomputer to start playing with this stuff. You can experiment today using the Python programming language and a free mathematical library called NumPy.
It's so accessible now.
It really is. You can go to mml-book.com and download the Mathematics for Machine Learning PDF completely for free. You can pull up YouTube and join the millions of people watching Gilbert Strang explain how these concepts snap together.
Highly recommend that.
Yeah, you can even open Google Colab in your browser right now, search for PCA with NumPy, and literally watch a high-dimensional dataset shrink before your very eyes using just a few lines of code.
You can literally see the math happen live. And knowledge is always most valuable when it's understood and applied. Taking that step to actually see the math in action, to see the shadow being cast by the data, it completely demystifies the entire field.
So true. So as we wrap up this deep dive, I want to leave you with a brand new, slightly provocative thought to ponder.
Oh, I love these.
We just spent this entire time proving that modern AI relies entirely on matrices, rigid equations, and linear algebra to learn and predict. Everything from language to movie taste is literally reduced to a dot product.
Yep, just arrows aligning.
But if you think about it, human brains clearly do not sit there doing massive billions of operations per second matrix multiplications just to recognize a friend's face in a crowd.
No, definitely not. Or to understand a joke.
Right. So are we actually building AI that thinks? Or have we just stumbled upon an entirely alien, rigidly mathematical way to perfectly mimic human results?
That is a heavy question.
Think about that the next time an AI effortlessly predicts exactly what you want. It might look like magic, but it's just the beautiful, relentless logic of the matrix.